Um, Hello, my name is Taras Semenchenko. I'm a PhD student at Taras Shevchenko National University of Kyiv. Today I'll present uh, our paper UAV to camera distance estimation based on the passive monocular locator. This research was conducted together with my academic supervisor Irina Yurchuk and my fellow PhD student Danil Mykola Obertan. Before we begin, I would like to say thank you to the conference organizers. It is a pleasure for us to be here. Um, Now let's move on to the first slide. This work focuses on UAV to camera distance estimation using a passive monocular locator. In simple terms, we estimate how far a UAV is from camera using only one optical image. The system is passive, meaning it doesn't emit signals like radar or lidar. It only receives visual information from a camera. In this research, we compare three groups of methods: geometry calibrated models, two-stage YOLO um, based pipelines, and an end-to-end multitask neural network. This problem is important because detecting a UAV in an image gives us 2D information. For practical use, we also need the missing third dimension, which is distance. The motivation for this work comes from growing use of small UAV. These targets can be difficult to detect because they are often small, fast, and may have low radar visibility. Active sensors such as radar or lidar can estimate distance well, but they emit signals. In tactical conditions, this can reveal the position of the defensive systems. Uh, Passive optical systems avoid this problem. A camera can observe these scenes without sending out any signal. For practical use, we also need to know approximately how far it is. In this work, we compare three method families. The first group is geometry calibrated models. They are based on the pinhole camera model. Distant object appears smaller and longer focal lengths make object appear larger. The second group is two-stage pipeline. First, YOLO detects the UAV and predicts its bounding box and class. Then, a classical machine learning regressor uses these outputs to predict distance. The third approach is an end-to-end multitask network. It receives the raw image and focal length metadata, then directly predicts both UAV, class, and also distance. The goal is not only to find the lowest error, but also to understand which approach is most realistic for deployment. For the experiments, we use a custom monocular UAV dataset with 4,074 annotated images and 5 UAV classes: FPV quadrocopter, Shahed 131, Zala 421, Lancet, and Zala Lancet Z52. The dataset includes 14 focal lengths from 14 millimeters to 400 millimeters. The maximum distance is about 984 meters, and the dataset allows us to test ranging almost up to 1 kilometer. All images have a resolution of Full HD. Each image includes a UAV class label, bounding box, focal length, metadata, and ground truth distance. This slide shows the distance distribution in the dataset. Most samples are at short distances. About 44% are in the 0 to 50 meter range. 24% are between 50 to 150 meters. 80% are between 150 and 400 meters, and only about 10% are beyond 400 meters. This matters because the hardest cases are also the least represented. At long range, UAV become very small, and even small localization error can lead to large distance errors. So the dataset has a long tail distribution. The first method is based on the physical geometry. The main idea is that the um, apparent size of an object depends on its real size, focal length, and distance. If the object is farther away, it appears smaller. If the focal length is longer, it appears larger. However, real UV images don't perfectly follow the ideal pinhole camera model. The bounded box area also depends on UV shape, UV angle, pose, annotation noise, and possible lens metadata errors. To reduce this bias, we apply calibration on the training split. We test two variants. The first uses known physical UAV size, which is theoretically grounded, but assumes the true size is known during inference. The second is size agnostic. It removes the explicit physical size term and learns a separate coefficient for each UAV class. The second approach is modular two-stage pipeline. The input is an RGB image with focal length metadata. First, YOLO V10 Nano detects the UAV and outputs the bounded box class and confidence score. These outputs are then converted into features for the distance regressor. The second stage predict distance using classical machine learning model. We compare SVM with RBF kernel, LightGBM, and also random forest models. This approach is practical because it separates detection from distance estimation. It is also fully autonomous because it doesn't need ground truth boxes at inference time. The third approach is an end-to-end multitask neural network. The model receives an RGB image resized to 384 by 384 together with normalized focal length metadata. The visual backbone is ResNet 80 visualized with ImageNet weights. After feature extraction, image features are combined with focal length metadata. Then the network has two output heads. One predicts UAV class and the other predicts distance in long space. The model was trained for 40 epochs with batch size 16, and also we were using Adam optimizer, learning rate which is 0.001 and weight decay 0.001. This method is simple at inference time. We use raw image in and the class and distance out. So for evaluation, we use a fixed 70-50-50 split for training, validation, and testing. The main metric is mean absolute error, or MAE, because it shows the average distance error in meters. We also report RMSE, median absolute error, MAPE, and the R squared. It is important that the methods are not evaluated in exact the same scenario. The geometry-based model use ground truth bounding boxes, so they show the upper bound potential under ideal localization. The two-stage and end-to-end models work automatically, so their errors include detection and classification mistakes. So this slide shows that error increase as distance grows. At short distances, all methods work better because the UAV is larger and easier to localize. At longer distances, especially beyond 400 meters, the UAV becomes very small. Even a 1 pixel bounded box error can cause a large distance error. The size-agnostic geometry model performs best overall, but it uses ideal ground truth boxes. Among autonomous methods, the two-stage YOLO pipeline are more stable and practical. The end-to-end multitask model degrades the most. The key point is that localization quality becomes extremely important as distance increase. Um, So this slide summarize the main findings. First, the size agnostic geometry model outperforms the size aware version. Um, the size aware model reaches of MAE of about 19, almost 20 meters, while the size agnostic version reaches 15 meters. This happens because a fixed physical UAV size is too strict for real flight. The size agnostic model handles this better by learning an effective class scale from data, while affine calibration corrects systematic errors. Second, the end-to-end model suffers from limited data. Around 4,000 images are not enough to jointly learn classification. and the long-range distance regressor is such difficult in such difficult conditions. YOLO performs better because it benefits from large-scale pre-training and already has strong detection features. To conclude, this work compares three passive monocular UAV ranging approaches on a custom dataset with distances up to almost 1 kilometer. The first takeaway is that passive monocular ranging can work at long distances, but it performance depends strongly on localization quality and data availability. The second takeaway is that geometry provides the best upper bound. The size agnostic geometry calibrated model achieved an Maya of 15 meters and R squared of 0.96 under ideal localization. The third takeaway is that the two-stage YOLO-based pipeline is the best practical choice. It reaches an Maya of around 22 meters in a fully autonomous setting, making it the most realistic deployment option among the testing methods. The end-to-end model performed worse, which shows that more data or better pertaining is needed before this approach can compete in long-range UAV ranging. There are several directions for future work. First, we need to expand the long range part of the dataset, especially beyond 400 meters. Second, cross dataset validation is important. Testing on other sensor environments and UAV types would show how well the results generalize. Third, the temporal multi-frame ranging could improve stability. Instead of using one image, future system could use short video sequences and motion cues. Fourth, the area-specific depth per training may help end-to-end model. Overall, this work shows that passive monocular UAV ranging is useful, but robustness at long range still need improvements. So I think that's it. Thank you for attention.